Okay, so what we're gonna do now is we're gonna apply the scalar, what we've learned from scalars and vectors into SJPO questions. So take a look at this question. Our plumb line is held steady and the mass of the plumb bob is M. So what I like to do for SJPO questions is I draw a diagram first because it can get very complicated. So the mass of the plumb bob is M. So what is going through my mind right now is that there's a weight of mg that's acting this way. And then since the train is accelerating in the forward direction at 0.5 grams, imagine there's a string there and there's a horizontal force of 0.5 g over here. So what you can notice from this is since the object is held steady and is in equilibrium, that means that the vertical force and the horizontal force due to the tension must be equal to the resultant force of the mg and the 0.5 g. So since this is a right angle, what we can do is to just use Pythagoras theorem to solve for t. And then we should get around 1.2 mg. So what you can notice is that there's actually a lot of similarities in facial physics as well. This type of questions can also be like similar to this. So try to apply what you learn from the notes into here as well. I'll also be pasting the solution up here for you guys to see. So if you guys need a break, you can also pause to see more carefully. Okay, now let's take a look at this question. So we have a 4 kg that rests on the smooth parabolic surface, which is given by the equation y equals to 2.5x squared. So when I look at a 4 kg, I know that the weight is going to be mg, which is m is equals to 4. And then we need to take into account like the forces in the diagrams. So we have a tension upwards due to the block V that's pulling the string, and we can't forget that there's also a normal contact force due to the surface. Since the sphere is in equilibrium, that means that the horizontal forces must be equals to the horizontal force due to the normal contact force, and the tension must be equal. So we know that T is equals to the mass of V times G. So by horizontal equilibrium, we can know that MBG cosine 60 degrees, because we are finding the adjacent, will be equals to the normal contact force and cosine theta. And theta will be this angle here, which we'll cover later. And then by vertical equilibrium, we also know that this will be the horizontal one. This is the vertical one. So we know that the tension due to the string MBG multiplied by sine 60, because we are going to find the op in this equation, plus the normal contact force and sine theta. Similarly, also this op force will be equals to the mass of the sphere mg. So what we're going to do is that we're actually going to manipulate this equation in order to fit this one. So in order to turn n cosine theta into n sine theta, what we're going to do is we're gonna multiply both sides of the equation by tangent theta. So that n will be able to get this. We're able to get the normal contact force times theta. So we need to learn how to manipulate equations like that as well. So after we got this equation, what we are gonna have to do is, we don't know the mass B, so we substitute this equation into this, and we'll get this equation once we substitute this one into this one. And then what we're gonna do is I'm just gonna divide by G, and we're just gonna be left with this simplified equation. So since we know what the mass of the sphere is, our only unknown in this case would be tangent theta. And in order to find tangent theta, the angle here, what we are going to do is we're going to find using this one, we're going to find the gradient using dy over dx, using differentiation. And by this, we'll get 5.0x, and when we substitute 5.0x with the x with 0.4, we'll then get 2.0. And we know from the O-level syllabus that tangent alpha, the tangent of the gradient, will be equal to 2.0. And then in order to find theta, we can notice is that this is a 90-degree angle. Since this is a straight line, we just have to minus off the angle alpha and the 90 degrees in order to get tangent 90 minus alpha. And using our trigonometric identities, we are able to know that tangent 90 minus alpha will also be equal to cotangent alpha, which is over 2.0. Sorry if this is a bit messy. And now that we know what the tangent theta is, which is cotangent alpha, we can just substitute this in order to get, since we know our mass, we don't know our mass B, but we know our mass and tangent alpha, we can just substitute tangent theta in order to get mass B as approximately 3.58 kg, which is over here. Again, I'll be pasting the solution over at the side, so you guys can check this out. Okay, now let's try and solve this question. We have a rope A subject to a force of 600 newtons at 60 degrees to the horizontal, and then rope B is put at a fixed angle of angle theta to the vertical. If the resultant force acting to the post is to be 1600 newtons vertically, what should the force T on rope B be? So, since there is only a resultant force acting vertically, that means there is no resultant force acting horizontally. So therefore, we can say that T sine theta must be equals to 600 cosine 60 degrees. Because we are looking at the op side, and we also know the hypotenuse. So using TOA, we are then able to get this one. And then the same for this one, but instead we use car. And then next we know that so this is equation 1. And the other equation we can get is the vertical force due to T and the 600 newtons would lead to 1600 newtons acting vertically. So thus we know that T cosine theta, because this is because we're trying to find the adjacent, which is here, and we know the hypotenuse. So this vertical force due to T is T cosine theta, which would be equal to 600 plus 600 sine 60 degrees would then be equal to 160. And when we substitute these equations, use simultaneous to solve, we should be able to get T equals to 1121 newtons, which is what you should get over here. I'll also be posting the answers right over here if you guys need the full instructions. So yeah, you guys can look at that. Okay, finally, let's take a look at this question. The upper end of a rope is fixed to a vertical wall. The upper end makes an angle of 30 degrees with the wall. When the lower end is pulled by a horizontal force of 20 newtons, what would be the mass of the rope? So the force acted opposite to the wall is actually going this way. So let's label this acting due to wall. And since it is also in our equilibrium, we're able to tell the horizontal force over here, the horizontal force due to the force due to the wall, will be equal to the force acting towards the left. So this is also 20 newtons. And since we know the angle here is 30 degrees, we are able to deduce that since sine 30 degrees is equals to 20 newtons divided by force acting due to the wall, then the force acting due to the wall is equals to 20 sine 30 degrees, which would be equal to 40 newtons. And then to find the mass of the rope, we also need to note that the vertical force acting outwards is also equal to the vertical force acting downwards. So to find the mass, what we have to do is to find the weight and divide it by the gravitational acceleration. So the vertical force due to force W will be equals to 40 cosine 30 degrees, which will be equal to 40 square root of 3 divided by 2, this is 3, then you get 20 square root of 3 So this vertical force here will be equal to 20 square root of 3. And then what we have to do is to divide 20 square root of 3 divided by G, the vertical force acting, the force due to the mass is also the same. We divide by G and we should get 3.5 kg. So the answer is D. I'll be pasting the answers out here for the same.